Hello everybody. Good morning or good afternoon, wherever you are. Today we're going to talk about time series analytics and specifically the operationalization of it. This is a part one of a series of webinars. So we're going to start with the basics today, and we're going to focus on a new module that is part of our architecture called TSA Analytics, and I'll take you through that today. Maybe for those that are not familiar with who we are Waylay. We're a Belgian company. We build software for IoT automation, and we have a specific vision and that we typically sell to customers that have already figured out the so-called connect and collect strategy, which basically means that they're in the IoT space and they have already decided on which hardware to put on their remote assets. Could be an engine, it could be an appliance, it could be a smart office, whatever, and have the ability to collect data. Now, the next step is, of course, to generate business benefits out of collecting that data. Nobody really wants to watch dashboards 24/7 a day. Typically, you want to take autonomous actions when something is wrong, or you want to trigger some IT systems as part of that. So today we are going to look at specific aspects of analytics, where we are going to look back at historical data that has been collected, typically enters our database as a time series of metrics, basically values of parameters that have a certain evolution in time. And we can use that as input to basically trigger a set of rules. For example, when we detect an anomaly, or we do a time to target prediction and assign a certain action to that detection. Right, so that's going to be the subject of today. Now, when we speak about analytics, analytics is a wide topic in the industry today. So I'm going to make a distinction between offline analytics and online analytics. Offline analytics is typically a process where people generate reports, do correlations with billing systems, for example, and typically it's done in an offline mode by data scientists that uses tools like Power BI or Tableau. Right, and the typical usage is not in an operational context, but more from a product management point of view, where you're going to look at, okay, how is the product used? Can I change my marketing strategy? Do I need to improve my some parts of the product that is not used or not well used, etc. That is not the subject of today. Today, we're going to talk about online analytics, where data is streaming in and where we are basically going to link a business critical rule for automation to that data, and specifically to the historical data. In order to realize this, there are two people that need to collaborate. On one hand, the business analyst that creates the automation rule, but also the data scientist in order to create an algorithm that is, that, for example, detects anomalies or outliers or does prediction. Right. So we're going to talk about this specifically in the context of our platform. Of course, when we talk about streaming analytics, we can make a distinction between real-time and near real-time. The subject of today is going to be cloud analytics, meaning that the data is pushed to the cloud, and in the cloud you're going to make decisions on what to do next. So the time frame that that you have in order to take actions is typically in the order of minutes, or hours or days, for example. That makes us a distinction between the real-time analytics that is typically executed on the edge, right? On a mini server that is located in the factory, for example, that has to take action within a couple of milliseconds or within a couple of seconds. There are a lot of companies that are working on that. This is not the subject of today. We're more in the cloud space, where we are going to act upon the data that is pushed to the cloud. Okay. So we've talked to various customers around this subject, and we saw a number of patterns and a number of challenges that they had in order to operationalize their ideas, their hypotheses that they have, and their algorithms that they have built in order to analyze the historical data and the time series metrics. So what we typically saw is a process that involves these 5 steps, right? And the first thing that people do is try to find on the market a service that provides an anomaly as a service, or people implement their own algorithm in Jupyter notebooks, for example. Okay, so that's typically a step number 1, where they have a hypothesis and they try to match it with a certain algorithm. But of course, then the data needs to be collected. The data needs to be stored. There's a typical iteration where you visualize the data to explore it, whether the data is behaving normally, abnormally, etc. Okay, so that also takes quite a bit of time. It takes time because you need to understand the data. You need to be able to understand how the data is varying over time, how the data is actually representing the real behavior of the asset that you're trying to monitor. And then you have to build a useful anomaly detection algorithm, for example, and test it against that collected data. You want to see how it behaves, you want to tune it and tweak it. Now, once that is done, you obviously need to wrap it in a service, right? And that service needs to be able to run that algorithm against data that is in your database. And on the other hand, needs to expose some sort of API, typically a REST API, such that you can integrate it with your business rules, okay? Such that, when data flows in, that data can immediately be processed by that algorithm to make a prediction or do an anomaly detection, okay? And then, of course, you have to build your rules on top of that algorithm, which basically means that you have to decide at which moment in time you're going to take action, which action you want to take. Maybe you need to pull some additional information from ERP or CRM systems like Salesforce or SAP, etc. And then you're going to take action at the appropriate time towards the appropriate endpoint. Okay. So as you can see, these 5 steps can take quite a bit of time, okay? And if we look at what some of the big vendors in terms of IoT platforms and cloud vendors are offering today, these are all disparate systems that people have to work with. The data scientist works in a Jupyter notebook, the business analyst works in another tool, then the database is managed by somebody else. So as you can imagine, by having these disparate systems, it takes quite a while before your hypothesis of anomaly detection is actually put into the field and actually producing the necessary business benefits. So that's the problem that we try to address with the Waylay platform, and we've made sure that this whole process can now be done in a couple of minutes. So how did we do that? Well, we have embedded inside our rule engine, which has been there for a while now, a new module that allows you to, on first hand, inside the same platform, look at how the time series data is behaving, basically data exploration, and at the same time create within the same platform the right anomaly detection and prediction models that you can immediately test against your business logic. And you will see this in the demo, how we can easily go back and forth between the actual business rule and the mathematics that are behind the anomaly or prediction models. And you can update them back and forth, so you can immediately see the effect of an update of your mathematical model on the business logic and vice versa. So it allows a very close interaction and integration between those 2 stakeholders that I mentioned earlier on, the data scientist and the business analyst. Okay. So how do we now approach it, right? I just want to make sure that you understand how we look at things when it comes to operationalizing rules or operationalizing analytics. Well, there are like 4 criteria that we always evaluate. Is it easy to explain what the rule is doing? And in this case, we're talking about analytics, which means that is it easy to explain to a non-expert how the algorithm is working? Right, that's for us, that's very important. Is it very easy to adapt it? Meaning that can I adapt my rule independently of my algorithm? Can I immediately see the effect of a change in the algorithm for anomaly detection on the rest of my business logic and so forth? So we need to be able to adapt it very fast and be able to understand if any changes have happened, how the end-to-end system is going to behave. Operability is, of course, everything that has to do with the daily updates that needs to happen. Maybe you have new versions of your algorithm or new versions of your business logic. You need to be able to instantiate that very easily with the click of a button without having to go to many hoops in order to make it live. You want to be able to test it on a certain group of devices. You want to compare those results, do A/B testing to see if you need to optimize either something in the business rule or in the anomaly detection algorithm, for example. And last but not least is all about scalability. Scalability is the ability to run your algorithms and your business rules against a large volume of data and large volume of devices. So you need to be able to do that very easily, and everything needs to be automated in the sense that if a new device type is added to your platform or your setup, then the rules and the algorithms need to be able to be instantiated for that device immediately. So these are the 4 criteria that we always use in order to evaluate and build our platform, in this case for time series analytics. So I'll use that throughout the presentation to explain what features we offer in order to be able to operationalize complex issues like anomaly detection and prediction. Okay. So let's start with the first one. The first one is the explainability. So we want to make it easy to build AI-powered rules, right? So what does that mean? Well, it means that we want to give the business analyst a very easy way of using concepts like anomaly detection, inactivity detection, forecasting, time to target prediction, and classification in its rule, right? The business analyst doesn't really need to know what is the algorithm behind it, but he does need to understand how in this case, our anomaly detection sensor is going to behave such that he understands which business logic to couple to it. And as you can see here, we have extended our library of software sensors and actuators with a number of analytics-powered nodes that the business analyst can easily drag into his rules and basically assign a certain action to it. In the picture you see here, a very simple rule that says if there's an anomaly in the server room, then basically send an email to a technician. Okay, so this is a very simple rule where the business analyst can easily use these kind of icons in his rule and can really truly understand what kind of logic needs to flow after the anomaly has been detected. Okay. So this is another way of expressing it. So the business analyst is working on the right-hand side. So he needs to be able to understand what the mathematics are doing to a point where he can basically decide which business rule needs to be assigned to that. While the data scientist is the person that works on the sensor itself on the left-hand side. So we believe that that person is the right person not only to build the right mathematical model, but also should decide how the anomaly sensor should behave, at which point in time it should flag an anomaly and which point not. And that really depends on the data that we're looking at. Okay. So yeah, people say, yeah, that's all fine, but I just want to do basic anomaly detection. Does it need to be, is it that complicated? Well, it really depends on what you're looking at and who is basically doing the work. So when we're talking about anomalies, it really could be that on the same set of data, you can have multiple anomalies depending on the time frame that you're looking at the data. For example, on the top, you see an anomalous outlier, right? You see a clear peak there when you zoom out of the data, right? And the zooming in and zooming out here is an important concept because you're looking at a certain time frame where you want to yeah, basically detect outliers or anomalies and want to take action on that, right? And it could be that the action that you want to take is different depending on the type of anomaly that you're seeing, right? On the top, you see a peak. Well, there may be a specific action that you want to assign to that peak because it's completely abnormal. While at the bottom, when we actually zoom into the data, we see a little bit of a pattern appearing inside the data. It could be, for example, a temperature sensor that measures the temperature, and the temperature during the day goes up and down. So you have a so-called seasonality pattern there. And it could be that in some cases, this pattern does not repeat itself. So that's another type of an anomaly, right? And there might be another type of action that you want to assign to that specific anomaly, right? And I'll give some nice examples in the rest of the presentation. Now, the question is, if you want to express all of this in mathematics, it's for sure possible. There are lots of mathematical tools out there available, lots of libraries where you can select the model, the algorithm that you want to instantiate. But the problem here is that these algorithms need to be tuned, right? There are lots of parameters. Some of them have even hundreds of parameters that you have to set in order to be able to use it for your specific domain and for your specific use case, right? So we're talking here about which granularity to choose, which aggregation, sampling rate, sensitivity, confidence levels, window sizes, and so forth, right? So all of that, well, if you're a data scientist, some of those people like to make their hands dirty and set all of these settings themselves. And that's fine if you have like 10 devices. But if you have hundreds of devices, you want to let the system figure all of this out, right? You're not going to watch every data point for these hundreds or thousands of centers every day. It's just too much work. You want to have the system figure out what are the right settings, what is the right model to use for the specific use case that you're trying to describe and want to take action on. And that's what our platform is capable of doing. So just to summarize here, what we mean about operationalizing anomaly detection, for example, is that how people express anomaly in a human language is much different on how mathematics looks at it. It really depends on what time frame you're looking at. Is it a peak outlier, or is it a pattern that we want to follow and we want to detect a break in the pattern, and that is our anomaly. So anomalies are perceived differently at different time scales. So that's a very important thing that you have to keep in mind. And there's obviously also a difference between the sampling rate, so at which the problems, the outliers present themselves, and then the time where you have to take action, right? In some cases, you want to take immediate action. In other cases, you have some time to to react, right? And maybe in some cases you need to get information from other systems before you can act. So it's very important to understand the context in which you are you're trying to apply your anomaly detection algorithm, and those are the kind of questions that pop up when you start thinking about operationalizing the hypothesis, the idea that you have around anomaly detection. So that's a bit high level. I truly understand that. So let's try to apply it for a specific use case, and you'll see how we're going to address that use case within the Waylay platform. So the use case that I'll use throughout this presentation is a specific use case called precision fish farming. So world, basically you have a number of fish tanks where fish are grown, and the whole goal of precision fish farming is to optimize the yield of the fish, right? So the bigger the fish, the fatter they are, the more the farmer can charge for them, and the more money he gets, right? But in these fish tanks, it is very important to monitor the quality of the water, okay? And the water quality has a direct effect on the yield, obviously. Okay, now, so the water quality is expressed with different metrics, the temperature, dissolved oxygen, pH levels, and so forth. So pH is basically the acidity of your water, and it really has all an impact on the growth rate of your fish, and there needs to be a good equilibrium to be able to guarantee and optimize the yield. Next to that, you also want to optimize the feeding for your fish, right? If you feed them too much, a lot of food is wasted, and it costs money. If you don't feed them enough, then your fish are not going to grow enough, right? So as you can see here with some of these examples, it is very important that we monitor the quality of the water, the quality of the food throughout the day, and as you will see, pattern detection for these use cases is very important, and will apply anomaly detection and prediction in this use case. Okay. So let's start with a few scenarios, right? Let's start with a scenario where you have a water pump. A water pump typically pumps oxygen within the fish tank, and yeah, the oxygen has an immediate effect on the acidity of your water. So let's say if that pump fails, then obviously you want to take action quite fast, right? In this case, you will see a use case where there's a possible blockage of the water pump, so it's pumping less oxygen into the tank. So you want to send an alert to the farmer such that he can intervene manually. Okay. A second scenario could be that we have a pH level anomaly. Right, it could be an outlier. An outlier could mean that we need to boost the pump to pump more oxygen into the tank because the acidity has increased too much. Okay. Now, what you need to know is that the acidity level, the pH level of a fish tank, is changing during the day. It has a seasonal pattern depending on the amount of light that falls into the fish tank. So if there's a change in the seasonality pattern, then the health of the fish is affected. Okay, so if something is changing within that pattern, we, for example, could send an alert to the farmer to check whether there's something blocking the light, or there's too much microorganisms into the water, and you need to pour some sort of medicine into the water to repair that. And last but not least, another scenario is more about forecasting or time to target prediction, as we call it, which is about, okay, if you have an automated feeding machine for your fish tank, you basically want to forecast when it needs to be replenished, where you detect that, okay, it's going to be, it's almost going to be empty, you need to refill it. And so you want to, in advance, a few days in advance, already automatically place an order to be able to order additional food if you're running low on inventory for fish food. Okay, so these are the scenarios that we're going to look at. So let me open now our time series analytics designer within our product. So let me start with the basics. So for those people that are familiar with the Waylay product, this is the Waylay dashboard. Very colorful, but you will see a new icon appearing at the bottom called TS Analytics. And TS Analytics will allow you to first explore the data, the historical data that has been retrieved for specific resources, and design a specific algorithm to be able to model the behavior of that metric. So let's take the first scenario that I mentioned before. Let's take the water pump. And the water pump is, as I mentioned, is pumping oxygen inside the fish tank. So let's assume our engine is behaving normally. So what a data scientist can now do is explore this data based on historically collected data, and can basically design or define a normal behavior of the water pump. So here I basically selected a specific window of my data where I consider the engine here or the pump behaving expectedly. Okay. So now the data scientist is basically going to create a model that is going to express this normal behavior of this engine. So for that, we let the machine figure out what is the best algorithm to describe that. So we click the auto configure button, and it's now going to analyze the data set and look for specific patterns. So there's a specific pattern around seasonality. Okay, we're not really interested in that at this moment, but we're more interested in a fixed type of model. Okay, so let me click start here, and now he's going to calculate the best model that is basically suited for our engine. Okay, so what he has now done is create a fixed model that hovers around 600 rotations per minute, but it does allow for some deviations around that. As you can see, our data set indicates that there's absolutely normal and no problem at all that we have a certain deviation in that rotation per minute. Okay, so if you're interested in how this model has now been constructed and what is behind it, well, here you can basically see all the mathematical details behind it. So we have a very simple model. It's an absolute value, but it does allow for a certain deviation of the metrics that are coming in. Okay, so now we have created a specific model, and now we're going to apply it to a separate data set where clearly the rotation is much lower than what we would expect as normal. Okay, so when we now apply our model to this data set and we click calculate, it's now going to test and basically validate the individual data points here against that normal mode. And obviously, because the deviation is much higher than the normal value, all of these values are being tagged, except for the ones where, yeah, the blockage of our water pump has been removed. Maybe the farmer intervened at this moment and the blockage has been removed. So the rotation is back at the normal rate. And at that point in time, the anomaly is gone. Okay. So for those that are interested in the mathematical aspects to it, you can also see the residuals here for every point against that normal model. Okay, so let's say we're happy with the anomaly detection model that we just created. Now we can store it. So we'll store that configuration. We'll give it rotation anomaly test for now, and let's save it. So now it's saved into the system, and now we can actually use this configuration in a rule. So I click this button, and now our rule designer opens, where we have already pre-populated our anomaly sensor with the right configuration. The TSA configuration is basically the configuration that we just created. That basically is a link to the configuration that is in the metadata now, and basically expresses what is the acceptable values for a normal behaving engine, and is basically capable of detecting anomalies. Okay, so so this is now pre-configured for the business analyst, and now he can start creating his rules. So he can, for example, now assign a specific actuator to that. So let's take SMS, for example, and he can basically say, well, I want to send an SMS whenever there's a state change from here, from my anomaly sensor. When there is an anomaly, I'm basically going to send an SMS. Okay, so this is how easy it is to collaborate between a data scientist and a business analyst between the rule. Okay, so now if we go back to our anomaly model, and if we change our anomaly model, let's say we update it, automatically this node will take the updated configuration of whatever we have stored. So if we change here, for example, the configuration to a new version, for example, the rest of the business rule does not need to change. It will automatically pick it up in real time. Okay, so you can actually store multiple versions of your anomaly model. Let's say you're still in the testing phase, so so that then you can actually use it for A/B testing. And once we're happy with the results, you can change the version to a production grade version, and use that in production, as I mentioned before. Okay, so behind this module is there's some artificial intelligence that figures out what is the best model to choose for your specific data set, and you can change that if you want. So today we have a number of out-of-the-box algorithms that we support, and if you're interested, you can even add your own. If you see fit. So if, for example, if you have a Python algorithm, a custom Python algorithm, you can easily plug it into the framework, and then it will show up here. But these are ones that we selected as being quite often used. Arima, Sarima, OLS, and so forth. You're probably familiar with those. So you can choose it manually, or you can let the system basically figure out which one is the best for you. Okay. So that's for the first use case. Just to let's summarize what we now saw. Okay. So let me get back to presentation mode here. So what we basically saw is the ability for a data scientist to easily visualize the data, right? And he has a tool to zoom in or zoom out depending on the time frame that he is actually looking at the problem, right? Maybe he's interested in a specific seasonal pattern, then he will zoom in at the appropriate time scale. If he's more interested in, for example, peaks, then he can zoom out and use that as a starting point for designing the algorithm. Right. Next step is then to create a model. So the system can figure out the appropriate model for you, and basically tries to match what you as a data scientist have tagged as a normal behaving condition, and use that as a kind of a semi-supervised model to be used for anomaly detection or prediction. Okay, so we have a number of out-of-the-box algorithms. We ourselves are not in the business of creating algorithms ourselves, but if you have to have, if you happen to have your own algorithm, or you want to use a different algorithm, yeah, it's very easy to plug in a Python library into our framework. Okay. So yeah, once you're happy with the model, you can change it as you see fit. or you can, like I said, let the system figure out the appropriate settings for seasonality, or if you have a fixed model for the deviations and so forth. Okay. So this is what we saw, right? The water pump failure, where basically it's very easy to go back and forth between the rule and the TSA designer, the time series analytics designer, for creating your mathematical formula and your algorithm for anomaly detection. And typically what we see is that this back and forth is typically can happen very fast in our platform, and that obviously accelerates the go-to market of your hypothesis for time series analytics detection, for example. Okay. As you have seen, we can store multiple TSA profiles. Though such a TSA profile can, well, it does embed the actual model, the sampling frequency, the anomaly detection settings. So it's closely coupled with each other, such that it's easy to update the model, the way that anomalies are fired, and so forth. And you can have multiple metrics, multiple profiles for the same metric, depending on the phenomena that you're actually looking at and the time window that you have chosen to zoom in. Okay. Yeah, obviously, if you want to tune and update the settings yourself, you can obviously do that. It's very readable. We have lots of documentation on our documentation page as well. For those that are not familiar with it, if you go to docs.waylay.io and you go to features, there you will find time series analytics, and there's quite a lengthy description of how the module works, what it does, and what is behind it. So such that if you want, for example, to update the confidence level, then you can tween and tune it as you see fit. Okay. Okay, so let me get back to the presentation here. We also have a bunch of sensors available to be used by the business analyst that basically harbor these algorithms and these anomaly detection models and prediction models. For example, you see here an anomaly sensor that you can use in your business rule. Okay, so within your business rule, you can still decide on a number of things. For example, the periodicity of when the algorithm should be executed. Okay, so this is here under advanced settings. You can, for example, decide, okay, I want to do a polling period of 900 seconds, which would basically mean that every 15 minutes you are going to execute the algorithm against a set of data that was recorded in the past for the last 15 minutes, for example. Okay, so this is something that you can still tweak with inside the rule engine itself, or the rule editor itself. Okay, so so this is what you can basically see here as well on the slide. You assign a specific TSA profile to your anomaly sensor. You select, okay, how much you want to look back in time if you're executing it in a more of a recurring batch mode, and everything is configurable in that sense. Okay. All right, so let's take the second scenario where, for example, we're more interested in the seasonal behavior of our data. I'll skip this specific use case here for time purposes. But the idea is basically that we have a set of data where we are interested in, for example, the seasonal pattern of I prepared it here, I think. We are interested in the seasonal pattern of our acidity level of our fish tank. Okay, so let's take the fish tank. And basically, we're going to take the seasonality level of our of the acidity. Okay, so we're going to load the data here, and we're going to zoom in to a specific part of the data set that that we retrieved. Okay, so as you can see here, we have a seasonal pattern of data where the acidity level goes up and down. But at a certain point in time, there is a deviation from that pattern. You see the peaks being lower, and here the seasonality is completely gone. So we want to be able to express this as an anomaly. Okay, so this is another example where we can basically select that. Okay, we expect this as a normal pattern. Again, we click the auto configure button. The auto configure will have analyzed the data and will have detected a seasonal pattern. We of course want to set a fixed model here that doesn't auto adjust itself. And we basically want to say, hey, this is a normal model of the pH levels of our fish tank. Okay, so if we now apply it to this data set and click calculate, you will see when specific anomalies will be triggered, right? And here you can basically see that there's a large difference between these outliers here versus what is expected. So these data sets will be tagged as anomalous. Here it's still okay because it's still within the normal ranges, let's say. So you can basically see that the algorithm has automatically adjusted for some small deviations here. But here the seasonality is completely gone, and basically these values will all be tagged as anomalous. Okay, so in this case we can now assign a specific rule to that, and for example, basically we want to send an SMS to a technician or raise an alarm into the system. We can easily assign it to that. Okay, now we can also create another model onto the same data set. And this is, for example, a model like this, where we want to basically be alerted when there are too much too high peaks. There's too much variation across an average value here. So that's a same time granularity, but a different model to model something different here. Here, for example, you see a fish tank that is not well tuned and tweaked. So here, basically the water pump that ingests oxygen into the tank needs to be steered to basically shave off these peaks that are very nefarious for the fish. Okay, so so that is something that where we can define a rule that says if we have these peaks, then steer the pump to put more oxygen in the tank. Versus the rule here where we clearly saw that there's a break in the pattern as what we see normal, but the action here is different. Here probably a human being needs to intervene to pour some medicine into the water because there's too much algae or microorganisms into the water that cannot be compensated by putting more oxygen into the tank. Okay, so as you can see, depending on the use case, you can assign a different rule and you can create a different model for your data. And all of this can be used in parallel. Okay, you can have multiple anomaly detection algorithms onto the same data set, and you can use them in parallel as different templates of your rule that you instantiate. Okay, so that's a quite powerful feature. Another example, which is more about time to target prediction, which is also supported by our platform, is the ability to do forecasting, where you basically create a model very similar to anomaly detection to model the behavior, for example, here of our automated feeder for our fish tank, where we see a gradual degradation of the feeder levels. They're getting low, and you want to know, okay, when does it hit the limit of 10%? Then I want to create an alarm such that I can order in advance additional food on the market at the right price, for example. So here we have a model that will model the downwards sloping trend of the automatic feeder, and we basically make a prediction in the future. Okay, when the certain threshold is going to be reached, and you see here also in like this light shade of gray the confidence level of this algorithm. So our platform supports that as well. Okay. So just to wrap up this presentation, as you have seen here in part one of our webinar here, which is all about operationalizing time series analytics, is that we have support for some basic cases. Typically, some people call it outlier detection, that basically detects out of limits. And the typical use cases that we have seen with various customers of ours is that these type of patterns are still very prevalent in the market, and that people like to use these quite simple ways of expressing a model and detecting outliers, because it's very easy to understand, it's very easy to update, it's very easy to trust these models in an operational context. So this slide gives some views of the typical patterns that we have seen for single variate anomaly detection, for example. We have seen cases where we have to express a model for missing data, where there's a specific gap in the data and then a specific action needs to be taken when some data is missing. It could be because the sensor does not have a good wireless connection to the cloud and needs to be repositioned. And that's a nice use case where missing data can indicate something wrong with the sensor in the field. Another case could be a sudden drop. We have also seen that in the example of our water pump that rotates suddenly slower due to a blockage. Well, that's another nice example where we can have an anomaly detection on such a behavior. Peak detection, as I mentioned in the beginning of the presentation, is a very common use case and really depends on the time scale that you're looking at. But we see that as a use case that is very much reoccurring in the IoT world. Intermittent drops into the pattern typically indicate something severe is going to happen in the future. So often people want to detect these intermittent drops as well. A break-in pattern is a very simple use case that we have seen also in the example of the pH level detection, where we have a seasonal pattern of the pH level during the day, and we see suddenly a break in the pattern and a specific action needs to be taken. In our case, it required an intervention of the farmer to check the water quality. Downwards trending data sets or upwards trending data sets is another very common use case, often used for prediction, but it can also be used for anomaly detection, for example. Okay, so these are the typical patterns that you can support with our platform. In part two of the webinar, that's going to happen probably after the summer, we'll talk about the more complicated use cases where we're going to apply machine learning for multivariate anomaly detection. Okay, so that's a bit out of scope for this initial part one of our webinar. Okay. So just to summarize, the way we look at the problem of IoT analytics is all about in the context of operational ability. So as I've explained in the beginning of the presentation, we have 4 axes on how we evaluate and explain the strength of our platform, right? The explainability is number one on the list. So do I and my colleagues understand the relation between the data and the analytics model and the rule? So for us, it's very important, especially because, yeah, it might be okay that you build an algorithm, for example, today, but within a month or within a year, you probably already forgot about it. So you need to be able to have a platform that expresses this model in an easy, understandable way for you and your colleagues. Okay. Adaptability is another important point about operational ability, which is the ability to quickly adapt it as my business context changes, or if I want to test multiple versions of my algorithm, I can easily compare them with each other. Okay. And operability is about being able to have a platform that allows you to version both the analytics models as well as the business logic that is coupled to it. And can I assess the performance, right? Can I step through it? Can I trace it? Can I understand when data is coming in? What is the effect on the algorithm? What is the effect of the rule that is coupled with it? And can I basically completely run through that to see how it is behaving in the field. And then scalability is all about, can I apply it? Can I apply my freshly baked algorithm against thousands of devices with one click of a button? Well, that's all supported with our platform today. So these were the unique capabilities that you can find into our product, and that is what I wanted to explain to you in this presentation. Okay, just for those people that are interested in using the TSA module, if you're already a customer with Waylay and you're using our multi-tenant cloud, you will see the time series analytics tile appearing in the dashboard, and you can immediately use it. You should have an update, have already had an update of your platform. So feel free to play around with it. There's a certain pricing associated with that, which is based on the volume of compute hours that you consume. And if you go to the stats tile in your Waylay dashboard, you will also see the amount of compute time that you have already consumed onto the platform. Okay, so the compute time is basically expressed as the amount of time that were used by the individual sensors in your rules, as well as the time that you use the TSA designer to train and configure your algorithm based on the data. Okay, what is not included, what is excluded from the computation here is the I/O. So retrieving and visualizing data is not included into the bill here. Okay, so that's important to know. This is also described on our documentation page. But yeah, feel free to experiment with it. If you have specific questions or you have a specific use case that you would like to explore together with us, feel free to contact me at tom@waylay.io, or if you prefer, you can also create a ticket in our Zendesk environment, and ultimately it will end up with me anyway, and I'll try to contact you for a further follow-up.